Identical particles, also called indistinguishable or indiscernible particles, are particles that cannot be distinguished from one another, even in principle. Species of identical particles include, but are not limited to, elementary particles such as electrons, composite subatomic particles such as atomic nuclei, as well as atoms and molecules. Quasi-particles also behave in this way. Although all known indistinguishable particles are tiny, there is no exhaustive list of all possible sorts of particles nor a clear-cut limit of applicability. See particle statistics #quantum statistics for detailed explanation. There are two main categories of identical particles: bosons, which can share quantum states, and fermions, which do not share quantum states due to the Pauli exclusion principle. Examples of bosons are photons, gluons, phonons, helium-4 nuclei, and all mesons. Examples of fermions are electrons, neutrinos, quarks, protons, neutrons, and helium-3 nuclei. The fact that particles can be identical has important consequences in statistical mechanics. As a result, identical particles exhibit markedly different statistical behavior from distinguishable particles. For example, the indistinguishability of particles has been proposed as a solution to Gibbs mixing paradox. Distinguishing between particles. There are two ways in which one might distinguish between particles. The first method relies on differences in the particle's intrinsic physical properties, such as mass, electric charge, and spin. If differences exist, it is possible to distinguish between the particles by measuring the relevant properties. However, it is an empirical fact that microscopic particles of the same species have completely equivalent physical properties. For instance, every electron in the universe has exactly the same electric charge. This is why it is possible to speak of such a thing as the charge of the electron. Even if the particles have equivalent physical properties, there remains a second method for distinguishing between particles, which is to track the trajectory of each particle. As long as one can measure the position of each particle with infinite precision, then there would be no ambiguity about which particle is which. The problem with the second approach is that it contradicts the principles of quantum mechanics. According to quantum theory, the particles do not possess definite positions during the periods between measurements. Instead, they are governed by wave functions that give the probability of finding a particle at each position. As time passes, the wave functions tend to spread out and overlap. Once this happens, it becomes impossible to determine, in a subsequent measurement, which of the particle positions correspond to those measured earlier. The particles are then said to be indistinguishable. Quantum mechanical description of identical particles. Symmetrical and antisymmetrical states. Here's an example to make the above discussion concrete. Using the formalism developed in the article on the mathematical formulation of quantum mechanics, let n denote a complete set of quantum numbers for specifying single particle states. For simplicity, consider a system composed of two identical particles. Suppose that one particle is in the state n1, and another is in the state n2. What is the quantum state of the system? Intuitively, it should be, which is simply the canonical way of constructing a basis for a tensor product space of the combined system from the individual spaces. However, this expression implies the ability to identify the particle with n1 as particle 1, and the particle with n2 as particle 2. If the particles are indistinguishable, this is impossible by definition. Either particle can be in either state. It turns out that we must have, to see this, imagine a two identical particle system. Suppose we know that one of the particles is in state and the other is in state. Prior to the measurement, there is no way to know if particle 1 is in state and particle 2 is in state, or the other way around, because the particles are indistinguishable. So, there are equal probabilities for each of the states to occur, meaning that the system is in superposition of both states prior to the measurement. States where this is a sum are known as symmetric. States involving the difference are called antisymmetric. More completely, symmetric states have the form while antisymmetric states have the form. Note that if n1 and n2 are the same, the antisymmetric expression gives 0, which cannot be a state vector as it cannot be normalized. In other words, in an antisymmetric state two identical particles cannot occupy the same single particle states. Exchange symmetry. The importance of symmetric and antisymmetric states is ultimately based on empirical evidence. It appears to be a fact of nature that identical particles do not occupy states of a mixed symmetry, such as there is actually an exception to this rule, which we will discuss later. On the other hand, we can show that the symmetric and antisymmetric states are in a sense special, by examining a particular symmetry of the multiple particle states known as exchange symmetry. Let us define a linear operator P, called the exchange operator. When it acts on a tensor product of two state vectors, it exchanges the values of the state vectors. P is both Hermitian and unitary. Because it is unitary, we can regard it as a symmetry operator. We can describe this symmetry as the symmetry under the exchange of labels attached to the particles. Clearly, so the eigenvalues of P are +1 and -1. The corresponding eigenvectors are the symmetric and antisymmetric states. In other words, symmetric and antisymmetric states are essentially unchanged under the exchange of particle labels. They are only multiplied by a factor of +1 or -1, rather than being rotated somewhere else in the Hilbert space. This indicates that the particle labels have no physical meaning. In agreement with our earlier discussion on indistinguishability, we have mentioned that P is Hermitian. As a result, it can be regarded as an observable of the system, which means that we can, in principle, perform a measurement to find out if a state is symmetric or antisymmetric. Furthermore, the equivalence of the particles indicates that the Hamiltonian can be written in a symmetrical form, such as it is possible to show that such Hamiltonians satisfy the commutation relation according to the Heisenberg equation. This means that the value of P is a constant of motion. If the quantum state is initially symmetric, it will remain symmetric as the system evolves. Mathematically, this says that the state vector is confined to one of the two eigenspaces of P, and is not allowed to range over the entire Hilbert space. Thus, we might as well treat that eigenspace as the actual Hilbert space of the system. This is the idea behind the definition of Fock space. Fermions and bosons. The choice of symmetry or antisymmetry is determined by the species of particle. For example, we must always use symmetric states when describing photons or helium-4 atoms, and antisymmetric states when describing electrons or protons. Particles which exhibit symmetric states are called bosons, as we will see. The nature of symmetric states has important consequences for the statistical properties of systems composed of many identical bosons. These statistical properties are described as Bose-Einstein statistics. Particles which exhibit antisymmetric states are called fermions. As we have seen, antisymmetry gives rise to the Pauli exclusion principle, which forbids identical fermions from sharing the same quantum state. Systems of many identical fermions are described by Fermi-Dirac statistics. Parastatistics are also possible. In certain two-dimensional systems, mixed symmetry can occur. These exotic particles are known as anyonts, and they obey fractional statistics. Experimental evidence for the existence of anyonts exists in the fractional quantum Hall effect, a phenomenon observed in the two-dimensional electron gases that form the inversion layer of MOSFETs. There is another type of statistic, known as braid statistics, which are associated with particles known as plectrons. The spin statistics theorem relates the exchange symmetry of identical particles to their spin. It states that bosons have integer spin, and fermions have half-integer spin. Anyonts possess fractional spin. N particles. The above discussion generalizes readily to the case of N particles. Suppose we have n particles with quantum numbers n1, n2, nn. If the particles are bosons, they occupy a totally symmetric state, which is symmetric under the exchange of any two particle labels. Here, the sum is taken over all different states under permutations p acting on n elements. The square root left of the sum is a normalizing constant. The quantity Minnesota stands for the number of times each of the single particle states n appears in the n-particle state. Note that n Minnesota equals n. In the same vein, fermions occupy totally antisymmetric states. Here, SGN is the sign of each permutation. Note that there is no term, because each single particle state can appear only once in a fermionic state. Otherwise the sum would again be zero due to the antisymmetry, thus representing a physically impossible state. This is the Pauli exclusion principle for many particles. These states have been normalized so that measurements of identical particles, suppose we have a system of n bosons in the symmetric state and we perform a measurement of some other set of discrete observables. In general, this would yield some result m1 for one particle, m2 for another particle, and so forth. If the particles are bosons, the state after the measurement must remain symmetric, i.e., the probability of obtaining a particular result for the m measurement is we can show that, which verifies that the total probability is 1. Note that we have to restrict the sum to ordered values of m1, mn to ensure that we do not count each multi-particle state more than once. Wave function representation. So far, we have worked with discrete observables. We will now extend the discussion to continuous observables, such as the position x. Recall that an eigenstate of a continuous observable represents an infinitesimal range of values of the observable, not a single value as with discrete observables. For instance, if a particle is in a state psi, the probability of finding it in a region of volume d3x surrounding some position x is as a result. The continuous eigenstates, x, are normalized to the delta function instead of unity. We can construct symmetric and antisymmetric multiparticle states out of continuous eigenstates in the same way as before. However, it is customary to use a different normalizing constant. We can then write a many-body wave function, where the single-particle wave functions are defined, as usual, by the most important property of these wave functions is that exchanging any two of the coordinate variables changes the wave function by only a plus or minus sign. This is the manifestation of symmetry and antisymmetry in the wave function representation. The many-body wave function has the following significance. If the system is initially in a state with quantum numbers n1, nn, and we perform a position measurement, the probability of finding particles in infinitesimal volumes near x1, x2, xn is the factor of n, comes from our normalizing constant, which has been chosen so that, by analogy with single-particle wave functions, because each integral runs over all possible values of x, each multi-particle state appears n times in the integral. In other words, the probability associated with each event is evenly distributed across n equivalent points in the integral space. Because it is usually more convenient to work with unrestricted integrals than restricted ones, we have chosen our normalizing constant to reflect this. Finally, it is interesting to note that antisymmetric wave function can be written as the determinant of a matrix, known as a Slater determinant. Statistical properties. Statistical effects of indistinguishability. The indistinguishability of particles has a profound effect on their statistical properties. To illustrate this, let us consider a system of indistinguishable, non-interacting particles. Once again, let Nj denote the state of particle J. If the particles have the same physical properties, the Nj's run over the same range of values. Let epsilon denote the energy of a particle in state N. As the particles do not interact, the total energy of the system is the sum of the single particle energies. The partition function of the system is where K is Boltzmann's constant and T is the temperature. We can factor this expression to obtain where if the particles are identical, this equation is incorrect. Consider a state of the system, described by the single particle states, n1, nn. In the equation for Z, every possible permutation of the n's occurs once in the sum, even though each of these permutations is describing the same multiparticle state. We have thus overcounted the actual number of states. If we neglect the possibility of overlapping states, which is valid if the temperature is high, then the number of times we count each state is approximately n. The correct partition function is. Note that this high-temperature approximation does not distinguish between fermions and bosons. The discrepancy in the partition functions of distinguishable and indistinguishable particles was known as far back as the 19th century. Before the advent of quantum mechanics, it leads to a difficulty known as the Gibbs paradox. Gibbs showed that if we use the equation Z equals Cn, the entropy of a classical ideal gas is where V is the volume of the gas and F is some function of T alone. The problem with this result is that S is not extensive. If we double N and V, S does not double accordingly. Such a system does not obey the postulates of thermodynamics. Gibbs also showed that using Z equals Cn, N, alters the result, which is perfectly extensive. However, the reason for this correction to the partition function remained obscure until the discovery of quantum mechanics. Statistical properties of bosons and fermions. There are important differences between the statistical behavior of bosons and fermions, which are described by Bose-Einstein statistics and Fermi-Dirac statistics respectively. Roughly speaking, bosons have a tendency to clump into the same quantum state, which underlies phenomena such as the laser, Bose-Einstein condensation, and superfluidity. Fermions, on the other hand, are forbidden from sharing quantum states, giving rise to systems such as the Fermi gas. This is known as the Pauli exclusion principle, and is responsible for much of chemistry. Since the electrons in an atom successively fill the many states within shells rather than all lying in the same lowest energy state, we can illustrate the differences between the statistical behavior of fermions, bosons, and distinguishable particles using a system of two particles. Let us call the particles A and B. Each particle can exist in two possible states, labeled N, which have the same energy. We let the composite system evolve in time, interacting with a noisy environment. Because the N states are energetically equivalent, neither state is favored, so this process has the effect of randomizing the states. After some time, the composite system will have an equal probability of occupying each of the states available to it. We then measure the particle states. If A and B are distinguishable particles, then the composite system has 4 distinct states, and the probability of obtaining 2 particles in the state is 0.25. The probability of obtaining 2 particles in the state is 0.25, and the probability of obtaining 1 particle in the state and the other in the state is 0.5. If A and B are identical bosons, then the composite system has only 3 distinct states, and when we perform the experiment, the probability of obtaining 2 particles in the state is now 0.33. The probability of obtaining 2 particles in the state is 0.33, and the probability of obtaining 1 particle in the state and the other in the state is 0.33. Note that the probability of finding particles in the same state is relatively larger than in the distinguishable case. This demonstrates the tendency of bosons to clump. If A and B are identical fermions, there is only 1 state available to the composite system, the totally antisymmetric state. When we perform the experiment, we inevitably find that 1 particle is in the state and the other is in the state. The results are summarized in Table 1. As can be seen, even a system of 2 particles exhibits different statistical behaviors between distinguishable particles, bosons, and fermions. In the articles on Fermi-Dirac statistics and Bose-Einstein statistics, these principles are extended to large number of particles, with qualitatively similar results.